Hi everyone. Today we are starting section 2.3, the limit laws. So far, we've been finding limits using tables and graphs. That works, but now we are going to learn algebra rules that make limits much faster and more precise, especially for polynomials and rational functions. In this section, you learn how to evaluate limits by factoring, use conjugates, analyze indeterminate forms such as 0 over 0, and apply the squeeze theorem to special limits. These tools are important because they help us compute derivatives in the next section. Before we get into the full set of limit laws, we need two simple but very important results. First result, the limit as x approaches a of x is a. Why is that true? Because the function here is f of x equals x. So whatever value x approaches, the function value approaches that same number. In other words, if x gets closer and closer to a, then f of x gets closer and closer to a. If you look at the graph of y equals x, it's just a straight line. X moves toward a number, the output moves toward that same number. Simple, but this idea is foundational for everything that follows. Now the second result. The limit as x approaches a of a constant c is just c. In other words, if you have a horizontal line like y equals 2, then no matter what x is doing, the output stays 2. These two facts may seem obvious, but they are the building blocks for all the limit laws that we're about to learn. Next, we'll start combining these basic ideas with algebra to evaluate more complicated limits. Now, we're going to state the actual limit laws that allow us to compute limits using algebra. Suppose that limit as x approaches a of f of x equals L and limit as x approaches a of g of x equals n. Then the following laws hold. For the sum law, limit as x approaches a of f of x plus g of x is the same as limit as x approaches a of f of x plus limit as x approaches a of g of x. So the result is just L plus m. In simple terms, the limit of a sum is the sum of the limits. For the difference law, limit as x approaches a of f of x minus g of x is the limit as x approaches a of f of x minus limit as x approaches a of g of x. So the result is L minus m. The limit of a difference is the difference of the limits. For constant multiple law, if you multiply a function by a constant c, you can pull that constant outside of the limit. So the limit as x approaches a of c times the function f is the same as c times the limit of the function f of x. And since the limit of f of x as x approaches a is L, so we have c times L. Constants can come outside the limit. For the product law, the limit as x approaches a of f of x times g of x is the limit of f of x times the limit of g of x, which is L times m. The limit of a product is the product of the limits. For the quotient law, the limit as x approaches a of f of x divided by g of x is the limit of f of x divided by the limit of g of x. So the result is L over m, as long as m is not 0. This condition is important because we cannot divide by 0. For the power law, if we raise a function to the power n, we can take the limit first and then raise it to that power. So the limit of f of x raised to the n power is L to the n. These laws allows us to break complicated expression into smaller pieces, find each limit, and then combine the results. Now, let's apply these laws to some examples. Example 1. Evaluating limits using limit laws. Question A. Evaluate limit as x approaches negative 2 of 3x minus 4. Using the limit laws, we can split this up. So this is the limit of 3x minus the limit of 4. For the first limit, since 3 is a constant that is multiplying to my function, I can pull out the constant 3. So I have 3 times the limit of x. Now, look at the limit as x approaches negative 2 of 4. Since 4 is a constant, the limit of a constant is always that constant, no matter what x is approaching. So this limit is simply 4. We already know that the limit as x approaches negative 2 of x is negative 2. So this limit is negative 2. So I have 3 times negative 2 is negative 6. Minus 4 is negative 10. So the limit as x approaches negative 2 of 3x minus 4 is negative 10. Now part B, evaluate the limit as x approaches 1 of 2x squared plus x minus 3 over x plus 4. Since this is a rational function and the denominator is not 0 at x equals 1, so we can use the direct substitution. We will substitute x with positive 1. For the numerator, I have 2 times 1 squared plus 1 minus 3. 1 squared is 1 times 2 is 2. 2 plus 1 is 3 minus 3 is 0. For the denominator, 1 plus 4 is 5. And 0 divided by 5 is 0. So the limit as x approaches 1 of 2x squared plus x minus 3 over x plus 4 is 0. That's how we use the limit laws to evaluate limits algebraically, much faster than using tables and graphs.